Good afternoon. Today's lecture is going to be covering percent dissociation and determining the pH of polyprotic acids. The percent dissociation or ionization is defined as the amount of the dissociated acid divided by its initial concentration. So we're looking at the change in the value for X divided by the initial concentration of the acid times the 100%. For any given weak acid, the percent dissociation will increase as the acid becomes more dilute. That's because we're not looking at a direct change. When we set up our Ka expression, we would have H3O plus times the A minus over the concentration of the HA initially, and when we would set that up, these would each be equal to X. So I would have the Ka multiplied by that initial concentration of the HA at equilibrium equaling X squared. So as the concentration gets smaller for the HA, the product of the Ka times the HA will be a smaller number. And again, we're taking the square root of that. So it's going to allow for the value for X to be larger in comparison to the initial concentration. Okay, so for our first example problem, we're going to take a solution of formic acid, 8.00 molar, that is 0.47% ionized in water. We're going to calculate the pH and the Ka value for the formic acid. So the first thing we can do is define X as being the 8.00 molar multiplied by the 0.47%. Remember to move the decimal over twice, and you end up with your change in X equaling 0.0376. So that will equal the concentration of the H3O plus and also the formate ion CHO2 minus. So when I set my equation up, I have the HCHO2 plus water forming H3O plus and CHO2 minus. Initially, again, for my rice table, I'd have 8.00 molar. I'd subtract X. Over here I have 0 and 0, and I would add X to each. In this case, because we know we have the 0.47%, we can subtract that off from the 8, and that would give us 7.963. And then I would have 0.0376 and 0.0376. So I can set up for my Ka for the first part, 0.0376, and I can square that and divide it by 7.963, and I would end up with a K value of 1.78 times 10, to the negative fourth, for the Ka value. And then to solve for pH for the second part, I can simply take the negative log of X. We've already defined what the X value is for that, so I don't need to rewrite the value. And that will give us a pH with two significant figures. That would give us 1.42. So pH equal to 1.42, Ka equal to 1.78. So let's change that to 1.8 times 10 to the negative fourth with significant figures. So for our second example, we have the value of the Ka for a 4.00 molar formic acid solution should be higher than, lower than, the same as the value of Ka of an 8 molar formic acid solution. So in this situation here, again, we're looking for the value of the Ka. So that will be the same as the value of the 8 molar formic acid solution. And the reasoning why, the only thing that changes the value is temperature. So that's the only variable that will change the value of the equilibrium constant. Next, we will look at polyprotic acids. A polyprotic acid is an acid with more than one ionizable proton. In solution, each dissociation step will have a different value for Ka. Please remember that only sulfuric acid is a polyprotic acid that is a strong acid. The first step would be completely dissociating. The second step, depending on the initial concentration, may completely dissociate or it may only partially dissociate. We'll come back and look at that in just a little bit. For every other acid that is a polyprotic acid, each step in the process will be a weak acid equilibrium system all into itself. When we have the equilibrium taking place for each step, please remember that this is taking place in the same container. There's just reacting with fresh water molecules to reform H3O plus and whatever the new anion is. As a rule of thumb, your largest Ka value will always be for the first equilibrium step. The reason why when we have this is because of Le Chatelier's principle. You will notice that in every single step along the way, we have additional H3O plus that is forming. And so as a result, the initial concentration that we have of H3O plus will still be present in each of these second equilibrium systems. And by Le Chatelier's principle, having that common ion essentially will force the reaction back towards the left, which would reduce the amount of PO4 3 minus or HPO4 2 minus in this instance, and that will reduce the value for the Ka as a result. So one other thing to remember, the overall Ka for the reaction, because this is a multi-step equation, if you remember your manipulations, the overall Ka would be equal to the Ka1 multiplied by the Ka2 multiplied by the Ka3. So usually when we're calculating pHs, we neglect any H3O plus concentration produced after that first dissociation step. Again, the reason why, like I was just saying, because of Le Chatelier's principle, the shifting that's occurring due to that larger concentration of the H3O plus in the first step means that the H3O plus produced in each of the subsequent steps will be very minute and therefore will not change the value for pH. Okay, so we're now going to determine the equilibrium concentrations for all species in a 5 molar phosphoric acid solution. So as we begin from the previous equations that we had on the last slide, we're going to start off by doing our 5% check to make sure that we don't need the quadratic. So I'm going to take my initial concentration, 5.0 molar, divide by 7.2 times 10 to the negative third, and when we type that in, that gives us a value of 694. Since this is greater than the 400, we know that no quadratic will be necessary. So we can go ahead and set up our rice table. So I have the R, I, C, and E. So I have 5.0 molar for my initial, and I would have 0 and 0 for the H3O plus and the H2PO4 minus. So I'm going to have minus X, and plus X. At equilibrium, 5.0 minus X, X, and X. So I can plug those values in here. So I'd have X times X divided by 5.0 equals 7.2 times 10 to the negative third. So when I solve for X, I end up with a value of 0.036. So if I were going to calculate the pH of the solution, I would just need that right there because the other amounts are going to be minuscule in comparison for H3O plus coming from the other two reactions. So I know that that would be my value of the H3O plus and also the H2PO4 minus. Now, we have a special circumstance that takes place when we look at our second equilibrium reaction, because now when we set up our rice table for this, hopefully you notice that my reactant, H2PO4 minus, is the same as my product, that we had in the equation above. So my initial concentration would also be the 0.036. I would have 0 for the HPO4 2-, but I also have H3O+, which was my other product from that first equilibrium expression. So in this situation, I would also have 0.036. So now when I solve for x in this case, I would have 0.036 times x divided by 0.036 equals 6.3 times 10 to the negative 8th. So my 0.036's would cancel when I set up my equilibrium expression. Sorry, I didn't set up my Rice table here. Again, I can ignore the change in x in this case because it is so much smaller for the Ka in comparison to the initial concentration. So whenever you have the second ionization equation for a polyprotic acid, because the initial reactant is the same as the product, NH3O is the same, those two will always cancel out, so you always know that the second anion concentration will equal the Ka for the second step. So I know that the 6.3 times 10 to the minus 8th will equal my concentration of the HPO4 2-. Now we have one more to go. Same thing, I can set up my Rice table here, and my initial concentration will be 6.3 times 10 to the negative 8th for the HPO4 2-. However, for the H3O plus concentration, it is still going to be the 0.036, because again, if I take 0.036 and I add 6.3 times 10 to the negative 8th, it is still going to essentially be 0.036. So I keep that in, I'd have 0, so minus x plus x plus x. So at my equilibrium, 6.3 times 10 to the negative 8th, x, and 0.036. Again, such a small value for Ka, don't need to include the x on this one or on this one because the change will not make any difference. So I can plug my values in, 0.036 times x over 6.3 times 10 to the negative 8th equals 4.2 times 10 to the negative 13th. So if I multiply the 6.3 times 10 to the negative 8th on both sides and divide by 0.036, we have our value for x. What's going on? Sorry, a little technical difficulty there. The value for x that we would get would be, in this case, 7.4 times 10 to the negative 19th molar for the PO4 3- concentration. So I have 7.4 times 10 to the negative 19th. I have 6.3 times 10 to the negative 8th. And then I have 0.036. And finally, the H3PO4, which would be the only other solution in the problem. Because our x was defined as 0.036, this would be 4.96 for its molarity. So that would be the only other one that we would have. We will now shift our focus to bases. A Bronsted-Lowry base is a species that accepts a hydrogen ion. For a weak base that dissolves in water, we have a generic equation of B plus H2O forms BH plus OH minus. The first thing I want to mention is that in this type of instance, the B is not your traditional metal hydroxide. It is going to be rather an amine-based compound. So think about ammonia, where we have some type of R group for the hydrocarbon, and then we have an NH2. On this side, we would have the R with the NH3 plus that would form. So you're looking for ammonia-based compounds, NH2s going to NH3s or NHs going to NH2 pluses, but you have some type of organic base that is taking place in this reaction. The base dissociation or base ionization constant is following the same type of pattern as your acid dissociation constant. We just label it as Kb instead of Ka. So we would have our products, BH plus and OH minus, divided by the initial concentration of the reactant, B. Just as the acid, the water is a liquid, so therefore it would be incorporated into that Kb expression. For these types of bases, please also understand that no base actually dissociates in solution, but the ions are produced when the base reacts with water. So again, this is the whole concept of ionization versus dissociation, where the ions are created in solution, not just separated. So you can see an example here with the reaction between methylamine and water. We have CH3NH2. We have the water where one of the hydrogens will cleave off and will attract to those lone pair of electrons on the methylamine and will form the methyl ammonium ion CH3NH3+, and we'll be left with the OH minus as a result. Okay, so we will now look at an example problem. We have dimethylamine, CH3(2NH), a key intermediate in detergent manufacture, has a Kb of 5.9 times 10 to the negative fourth. What is the pH of the 1.5 molar dimethylamine solution? So I'm going to set up my reaction here. So I have CH3(2NH) plus the H2O. It is going to form CH3(2NH2 plus and OH minus. So notice they're asking us to solve for pH, but we will get a concentration of OH minus in solution. So we'll have one extra step that we're going to have to do in order to solve this problem. So we can set up our Rice table. So I have 1.5, I have 0 and 0. So I have minus x, plus x, and plus x. And at equilibrium, 1.5 minus x, x, and x. So in this case, doing our 5% check, exponent for 1.5 would be 10 to the 0 versus 10 to the minus 4. My difference is greater than 3, so no quadratic would be necessary. So I can plug in my value. 5.9 times 10 to the negative fourth equals x squared over 1.5. We can assume again that x will be approximately 0. So I can multiply both sides by 1.5. And when we do that, that gives us 8.85 times 10 to the negative fourth equals x squared. And from here, taking the square root of both sides, we end up with a value for x equal to 0.0297. And if I take the negative log, I can get the pH. So if I take the negative log of x, that will equal 1.52. And finally, to get to the pOH, I would take 14 minus that value for pH, which will give me 12.47.